You have probably seen that massive concrete dome rising above the tree line while driving down the highway, or catching a glimpse of it on the news. If someone asked you what that structure actually does, you might say it keeps radiation trapped inside, or maybe that it was built to survive a plane crash. While both of those answers are partially right, neither one explains the real reason that dome exists in the first place. The true purpose of the building comes down to what happens when everything goes wrong at once. You have to stop thinking of the dome as a standard building because it functions as the final line of defense between a massive pressure event and the outside world. To understand the engineering, we have to ask how a layer of concrete can stop a force strong enough to tear solid steel apart. To get the logic right, we need to strip away the idea of a building entirely. Most people look at the dome as a roof over a reactor, but it is actually a sealed pressure vessel designed to act like a giant reinforced flask. Its only job is to hold in an enormous amount of internal force if the system fails. The outer shell is thick, reinforced concrete, usually between 3 and 5 feet deep. Because concrete is great at being squeezed, but terrible at being pulled, engineers run a dense grid of steel rebar through it to add tensile strength. On the inside face, there is a heavy steel liner that acts as an airtight seal, the piece that actually keeps gases from escaping, even if the concrete develops tiny cracks under extreme stress. The clever part involves high-strength steel cables called post-tensioning tendons running through conduits inside the walls. Workers pull these cables to enormous tension before locking them in place, forcing the concrete into a permanent state of compression. Any internal pressure trying to push outward has to fight a wall that is already pushing back. That design choice changes everything about how the structure handles a crisis. Engineers call the broader strategy defense in depth, and the dome is the fourth barrier in that chain. The first layer is the ceramic fuel pellet itself, followed by the metal cladding around the rods, then the thick steel reactor vessel. The dome only activates once those first three have been completely overwhelmed. One common mistake is thinking the dome blocks radiation during normal operations. Most of that work happens at the reactor vessel level. The dome is just waiting for a catastrophic event that engineers hope never happens. And the biggest threat it was built to handle doesn't come from the outside. The real danger is already sitting inside the building. The scenario that keeps nuclear engineers awake at night has a specific name: a loss-of-coolant accident, or LOCA. To understand why this is so dangerous, we have to look at how the cooling loop actually functions. The reactor core runs at an incredible temperature, and the pressurized water acting as a coolant absorbs that heat to carry it away safely. If a major pipe in that loop suddenly snaps, the water inside is no longer under high pressure. When that liquid hits the lower pressure of the containment building, it flashes into steam almost instantly. This isn't a small leak or a steady hiss of vapor. It is a violent, massive expansion that sends a shockwave of pressure slamming into the interior walls of the structure. The dome has to survive that spike immediately, not over several minutes, because the physics of the phase change happens in a heartbeat. We actually have real-world proof this logic works from the 1979 accident at 3 Mile Island. The reactor core suffered a partial meltdown, one of the most catastrophic failures possible, yet the containment building held firm and prevented a major radiation release. The system did exactly what engineers intended. Different reactor designs handle that sudden pressure spike in their own ways. Pressurized water reactors, or PWRs, rely on a large, dry containment volume where the dome acts as a massive pressure buffer, letting the waves spread out and lose intensity. Boiling water reactors, or BWRs, route the steam into a suppression pool, a large body of water in a torus-shaped chamber beneath the reactor. When hot steam hits that water, it condenses almost instantly, dropping the pressure before it can damage the outer shell. Same problem, two different physical solutions. The 2011 disaster at Fukushima is often misunderstood, but it actually highlights how these specific layers perform under pressure. While the images of the explosions were devastating, the primary containment domes likely did their job and stayed intact. The explosions actually came from hydrogen gas building up in the outer reactor buildings, which are separate structures from the reinforced domes. It is a critical distinction to make because the domes performed as designed, while the secondary systems around them were what failed. If you want to keep seeing the hidden logic behind these massive machines, hit subscribe as we break down the world one mechanism at a time. We know the dome can handle a massive internal explosion, but engineers also had to account for threats coming from the outside. This is where the construction gets even more extreme. You might have heard that these structures are built to survive a direct hit from a jet, and while that is true, the word survive means something very specific in engineering terms. When a large aircraft strikes a wall, the energy doesn't arrive as a single clean punch. It's a distributed, high-speed crush involving a crumpling fuselage, igniting fuel, and a spray of debris. Full-scale impact tests in the United States and Germany, where engineers literally fired jets into concrete targets, showed that a pre-stressed wall with enough mass doesn't need to deflect the plane. It just has to outlast the event. Think of it less like a shield blocking an arrow, and more like a mountain absorbing a landslide. The dome wins because the plane runs out of energy long before it punches through. Safety comes from mass and compression, not just hardness. After Fukushima, the industry didn't just patch the old designs. Engineers asked what would happen if you had no pumps, no electricity, and no one at the controls. That thinking led to designs like the AP1000, which features double containment walls and a fully passive cooling system. If power goes out and backup generators fail, a massive water tank on top of the dome uses gravity and natural heat flow to keep the core cool. No pumps, no switches, no people required, for 72 hours or more. That is the real leap in modern engineering. We aren't just building thicker walls. We are designing systems where the physics handles the emergency automatically. Most issues inside a plant are caught and stopped at the first or second layer of defense, long before the dome is ever needed. We build these massive concrete structures because engineers insist on a final backstop that works even when everything else has failed. The dome isn't just a precaution. It is physical proof that the worst-case scenario was already factored into the blueprint. So the next time you spot that dome on the horizon, remember you aren't just looking at a building, you are looking at the final answer to a question engineers have been refining for 70 years, which is what it takes to contain the worst possible outcome and still walk away safely. The solution is a clever mix of concrete, steel cables, a suppression pool, and passive physics backed by a whole lot of redundancy. If you want to keep pulling apart the hidden logic inside the machines and structures most people walk right past, hit subscribe. We break the world down one mechanism at a time. Thanks for watching, and I'll see you in the next breakdown.